Okay, so good evening, everyone. So, this is the third presentation of the series. So, we have two students who explored on how artificial intelligence can be leveraged to analyze and predict the factors that determine the winner of this popular online game, Basketball Hedge. So, let's see now what they have to say. Over to you guys.
Yeah. Hi, my name is Rishi, and this is Shamik.
Yeah,
Um, yeah,
my name is Shamik Saraswati. I study at Inventure Academy, Bangalore. I'm in grade 10.
yeah. My name is Rishi, and I go to Scotch College. In Western Australia. Yeah. So yeah. Good evening, everyone. This is our presentation.
Next slide.
Yeah.
Next slide, please.
Yeah. So today we'll be presenting our research on gameplay analysis in the online game Basketball Heads, with a focus on tracking player behavior and movement patterns. In many games, especially fast-paced ones, players often rely on intuition. This research project explores the use of motion tracking and data visualization techniques to analyze and enhance gameplay performance in the online game Basketball Heads. Next slide. Oh no, not back. Yeah. So to explore this, we chose Basketball Heads, a browser-based 1v1 basketball game where players control characters with exaggerated cartoon heads. The game is simple to pick up. Matches are fast-paced, and winning often depends on your timing, position, and predicting your opponent's movement. This made it a good candidate for motion tracking and gameplay analysis. We recorded the gameplay footage and applied Python script to extract the movements of the ball and the players, with the goal of discovering patterns that lead to consistent wins. So our problem statement is so our goal is to optimize gameplay in the web game Basketball Heads by identifying key patterns in player and opponent behavior that lead to more wins per round. Through this project, we aim to create a general method to which others can apply to other video games to optimize gameplay over a wide variety of action games. Next slide. So our method draws on existing research in gaming and computer vision. In 2018, a meta-analysis by Bidu and his colleagues showed that video games can improve specific cognitive skills. RTS games improve flexibility, FPS games increase task switching speed, and simulation games enhance real-world decision-making skills. This supports our understanding that gameplay can be studied seriously to enhance both in-game and cognitive performance. Paul and his colleagues in 2011 introduced the idea of theory crafting in World of Warcraft, exploring how players use data modeling to refine their strategies while playing the game. We are applying the same logic to Basketball Heads, transforming our instinct-based play into a data-driven approach. Zhang and his colleagues in 2020 also proved an effective hand tracking technique that could be done with just a standard webcam and OpenCV code. This showed us that it is possible to extract useful motion data from something as basic as screen recording without expensive sensors or tools. Next slide. Yeah, so in this project, we've developed an object-based tracking system to track gameplay in Basketball Heads. We've also created and collected and analyzed our own coordinate data from our own gameplay in CSV files to evaluate player accuracy and shot patterns. We have also analyzed the data to figure out the most important skills to improve gameplay. We've also demonstrated a replicable tracking approach using only standard video input. Next slide. Yeah, so this is how we went about doing our project. So first, we decided to play and store videos by screen recording them. And then through code, we would extract the data from each round, which included the coordinates of player 1, player 2, the ball, both goalposts, and relative positions among these objects. Then we would extract the game statistics from round coordinates so that it was more organized data. And then using this data, we would be able to use code to create graphs to find patterns. So we've used 1D heat maps, median X position, player speed, number of attempts, and ball possession. And then using this, we would code and we would find statistics, data visualization to come to a conclusion. Next slide. So our data set consisted of 30 rounds of basketball heads, and it also consists of individual player stats, such as speed, possession, and median X. Our independent variable was the outcome of the game, meaning who won or who lost. Next slide. So this is an example of our data set. So the amount of rounds, so the round number played, the amount of time in possession, the speed, the attempts, median X, and whether the player won or lost the game. Next slide. For finding the ball, we used a color detection program to detect the ball while it was moving across the court. You can see in the image shown. Since the ball consists mainly of a single color, which was orange, we used a color mask to isolate the color. You can see the result in the image above. We also decided to merge all the overlapping or nearly overlapping bounding boxes of the color mask. Next slide. For detecting the player, we used a CSRT method, where we calculated the initial coordinates of the player and updated the coordinates with every frame. These coordinates were then stored in a CSV file, which we could use to analyze later. Next slide. Yeah. So for our goalpost coordinate detection method, so one of our more technical challenges that we tackled was detecting the goalposts in each frame of the gameplay video. Since the camera shifted with the ball during gameplay, we couldn't use fixed coordinates for the hoops. So instead, we used the ball's position as a reference point to find the locations relative to the ball for the hoops. So here's how our method works. So first, we detected the ball's X and Y coordinates in each frame. And then we calculate the left goalpost by shifting about 10.6 ball widths to the left. And you can see there. And for the right goalpost by shifting 11.5 ball widths to the right. Vertically, both goalposts are estimated at 3 ball heights below the ball's current position. We arrived at these numbers through trial and visual testing, and they gave the most accurate match to the actual hoop positions on screen. This scaling approach makes our goal detection adaptive, and it can adjust the ball's movement in camera view, allowing us to track the goal's areas accurately, even as the gameplay environment changes. Next slide.
Yes, so now we had a program which could take in an input video of the game basketball heads and output a CSV file with the coordinates and relative coordinates of the ball, player, and opponent. Now, basically, the next stage of our program would firstly, as you can see in the flowchart, take in the CSV file, detect the number of goals, the number of rounds, and the winner for each round. And for each round, it would firstly generate the ball heat map, player heat maps, and speed time graphs, which you will see in the next slides. And also calculate, can you, and also calculate the median X position, the number of attempts, and the speed of the players. Next slide. So the first question was, how do we find the number of goals? And we use the method we used earlier in our previous method. We defined the goal as a period of 2 consecutive frames in which there is no ball, since when you score a goal for a period of time, the ball disappears when it teleports. And to determine the winner, we just see on the last frame of the ball, it's on the left or the right hand side of the screen, because if the player scores, for example, he'll score the left goal, so the ball would be on the left. Next slide. Now, as mentioned earlier, the program would create a 1D heat map of a ball, the ball's X position. In the heat map, you can see there's a yellow line at around 600. That's the initial position of the ball, and it's yellow because it's high density since it spent a lot of time there. This was a relatively short round. There was only one shot made at around 130 to 195, which is the left goal. You can see it also had some density, but in the middle, from 200 to 600, there's not a lot of density, which shows that. It shows that it doesn't spend a lot of time in the middle, but spends a lot of time on the edges of the court. Next slide. Yeah, so this is the 1D heat map of the player for the same game. Again, the areas of high density. The heat map is flipped here. In the game, the player lost as the opponent made the first winning shot. You can see the yellow line around 975 and three key areas of high density and low density in the middle, which is similar to the 1D heat map of the ball. Next slide. Now we analyze this with longer games. Here we can clearly see in all the areas of high density, where the players stop usually to watch the ball, and in all other areas there's relatively low density. Next slide. As mentioned earlier, we also worked on detecting ball speed. Here you can see before goal one of one of our rounds, the frame is on the x-axis time, while speed is on the y-axis. The speed is erratic; it varies a lot, but you can kind of see the arcs as when the ball moves across the court. There's not much to analyze from this graph, but we understood that the speed can vary randomly as the game also proceeds randomly. Next slide. Now, the number of attempts was the number of times the ball would cross the midpoint of the screen with the threshold velocity. Basically, if the velocity was high enough and the ball goes from one side of the screen to the other side of the screen, we consider that an attempt. To calculate ball possession, we used a simple formula. The delta is an indicator function. So it's basically for a given player the percentage of frames in which the ball was closer to the player. And we observed initially that in many of the goals, the player closest to the ball wins. In our first three rounds, for example, ball possession was 70%, 98%, and 68%. Next slide. During the stage, we also wondered whether the ball would throughout the game remain closer to the winning goal, which is like goal possession in a way. The answer was no, since the course of the game could rapidly change and it was random. There was no correlation whatsoever. Next slide. Next slide. Yeah. Now, after that program was made, we did step three data prediction. As Rishi showed earlier, there was a CSV file containing the speed, attempts, ball possession, normalized median X position, basically to ensure there's no bias between player and opponent, an outcome which is one for win, zero for lose for 28 players. The outcome, win or lose, was an independent variable. Next slide. We created a model with an accuracy of 85.71% based on ball possession, which basically means that if ball possession is more than zero point 0.5, there's an 85.71% chance of winning. We found out this using a decision tree, which is basically an algorithm. A decision tree model is an algorithm which, given a CSV file, finds the most optimal way by minimizing something called the Gini coefficient, basically finding the most optimal way to classify data and predict the data. Next slide. Apart from decision tree models, we also use two other models called random forest and logistic regression. We all In each of the models, we also got to rank the importance of the features to contributing to contributing to player victory, player outcome. And in the three models, we also compare different statistics. And how we did this was basically we repeated the same thing with multiple different times, since when we do this, 20% of the data is randomly chosen as test data. And so to ensure bias is minimized, we did this many times and took the average. Next slide. So here you can see the tables. So there's three models: decision tree, random forest, and logistic regression. You can see in general, decision tree is the better model. It has higher accuracy, precision, good recall specificity, and the F1 score. The F1 score is basically the harmonic mean of precision and recall. In the second table, you can see the rankings. It's We observed that in all three models, the rankings were basically the same, and ball possession greater was always the most important feature by a wide margin. Secondly, the meter next position. Thirdly, the number of attempts made, and fourthly, the average speed. Next slide. In conclusion, we have developed a reasonably accurate system, around 80 to 85%, in determining game outcomes using clear data, which is very encouraging. Moreover, we have been able to isolate ball possession as the most important factor contributing to victory. Next slide. Limitations: we have limited ourselves to the first level, and we haven't really analyzed specific tactics like dunking or dribbling, which are rare but do exist, and not considered the effect of power ups, which are also relatively rare. They're basically special effects that occur sometimes during rounds. But nevertheless, all in all, the study has provided useful information into the importance of different factors in determining player outcomes, and is an important step towards more accurate models. Thank you for listening to our presentation.
That was a real good presentation, guys. So you guys demonstrated the potential of AI-driven insights to enhance the understanding of this game. So this would definitely pave for the way for more advanced applications in gaming analytics and strategy development. So sure, looking forward to that. Okay. So for questions, please leave the comments in the YouTube section, or you guys can reach out. Okay. Thank you, guys. We can now stop.